Okay, so this is the motor driver class, how motorsport works. I'm Joe Sullivan. I'm an EPICS software developer at the APS in the B-Mind Controls Data Acquisition Group. Okay, so the talk, I'll describe the high level motorsport framework when you're developing support for motor hardware. Kind of breaks down to two levels: the controller level and then the access level. Bit of history: the original ASIN motor was released about 2006. Collaboration between Diamond and the APS with Peter Dennison, Nick Reese, and Mark Rivers. The current version that I'll be describing, we call that Model 3 of the ASIN motor, and the primary developer was Mark Rivers. So a lot of this talk will be referencing other material. These are my two primary sources. Model 3 EPICS motor driver support that was given by Mark Rivers in 2012. And I also referred to a Doxygen-generated web page, ASIN motor class documentation that Mark Rivers generated about 2012 also. So the EPICS motor support. Kind of an overview of the top level. Object is the motor record. That's a standard record that's been around a long time, so it has a lot of support by EPICS clients. The next layer is device support, and that's just the layer that communicates between the motor record and the low-level driver. And then, of course, the driver. That actually does not know it's talking to a motor record. It's talking through ASIN in a more general way. So it's basically the interface between ASIN and the hardware. So the current framework that we recommend new device support be written in is ASIN motor, otherwise known as Model 3. One aspect of Model 3 is that you have access to the ASIN port driver, which you can use to extend support for hardware outside of what the motor record provides in a standard way. So now I'll pretty much get into ASIN motor from here on out. The Model 3. It's been available in the Synapse motor module since 2011. It's a C++ model. It has two base classes, the ASIN motor controller and the ASIN motor access. The base classes provide much of the functionality. You only need to write device-specific implementations. And also, as I referenced before, the framework allows for controller-specific features that aren't necessarily supported in the motor record. It also, in addition to that, it has a direct support for coordinated motion via profile methods in the API. So this chart kind of describes the flow or the class inheritance. You start with the ASIN port driver, which ASIN motor controller is derived from, and then you derive the motor-specific class from that. That's the controller. On the axis side, the motor axes are derived from this base class, ASIN motor axis, and you would derive an instance of this class for each physical axis that you have in your controller. Just a brief divergence in the synapse where you'd find some of this stuff. The code is all in the ASIN motor module. When you build that, it does require these 4 other standard Synapse modules if you were building outside of Synapse. ASIN, BSDA, IPAC, and the sequencer. If you're in the motor module, this is kind of the path to the code with the specific files being, this is the device layer, is all on this. It is a this isn't C++ because it has to interface between C++ and the motor record, which is written in C. The ASIN motor base classes, which are, again, these are the actual files. There's one C++ file and one include file. So now the motor driver code that implements controller-specific methods from the base classes is kind of the standard file naming template that I guess we'd recommend. You have the name of your specific hardware with motor driver C++, the include file, the DBD file. It's basically the only 3 files, at a minimum, you would need to implement a controller. So getting to the ASIN motor controller, the constructor, what does that do? It creates the object, which again all derives from ASIN port driver, but it gives you the code that implements the real motor controller. So what you end up doing there is you're initializing actual hardware. You also call a access class constructor for every motor channel that's requested in the create controller function. You also have to start a puller task that will gives you the periodic updates on the status of the hardware. You can also implement the non-motor record features at this point using ASIN port driver calls. And also this way you do the profile methods. I'm not going to cover profile in this talk. Really, I'm going to focus on the motor record, what you have to do right to support the motor record. So I'm going to use as an example some hardware that's in the motor module right now. This is the ACR motor controller. So I'm using that code as an example. I think it's a recommended example to use if you're writing your own. So at the very beginning, what are we doing from IOC and NIT? We're calling the constructor, basically. The call will look like this. You're creating the controller, the arguments, the port name you want to create, the ASIN port they're going to communicate with the hardware, on that you've already created, the number of axes that you expect to support on this controller, active polling time, and idle polling time. What that code will look like is this. You have the create controller, and basically you're just instantiating a new instance of the ASIN motor controller. So the details of that, I think it kind of mirrors the create controller call. Just passing them through to the constructor. So this is the constructor. Again, these are the calls. These are the arguments from the create function call, and this is where you create the base class from the motor controller. Not all these arguments get past the motor controller. I'll go into these right here. I guess this is just at this point, I like to say this is copied from the Doxygen web pages. Number of axis, number of parameters. This is really, if you're familiar with the ASIN port driver, these arguments are pretty much the same, are passed directly to an ASIN port driver. So these are the same arguments you would call on an ASIN port driver object creation. I think it is worth describing these arguments specifically as it relates to ACR. I guess I'll go back and forth here. Going through these, the port, you have the port name, which is what you're creating, the number of axes, which you are getting from the create call, number of parameters. These are, you'd get a number of parameters with the base class, and this will be ones that you are adding over and above what you would have with the base class, which are, I think, nominally, the motor record parameters. The next two arguments are bit masks. These are, when you call ASIN port driver, it masked off all the interfaces it supports, and this will be masked over and above what you get with the ASIN port driver. The ASIN flags, there are two, whether you want this driver to be blocking or not, which is to say asynchronous, and whether or not there can be multiple devices on this port, which I believe allows for using the address field on the ASIN port. Whether you want ASIN to auto-connect to that port, and the task priority and stack size. These are only used if it's an asynchronous, you're going to create a new thread for this driver. So, yeah, in the ACR's example, what Mark was saying is that you do have additional parameters on this driver outside of the motor record, and the one that is implemented is this unsigned N32 digital ASIN interface. It's saying it can. You want this driver to block. It's asynchronous. and it is you could have multiple addresses to the ASIN port. I think usually you do want your drivers to be asynchronous. I think you want them running in their own thread. So again, this is the constructor. So, and this kind of, I want to give an example of what it looks like to create unique parameters for a controller. And this is, again, ASIN port driver call, so you have to be familiar with that interface for these calls. But basically, you have a string that I think is going to be referenced by the record, the interface you want to use, and the function you want called. The other thing with the constructor you're going to do in there is you're going to connect, is actually do the connection to the hardware. Octet sync IO, that's going to be an ASCII serial connection. Another thing you can do in these constructors is, once you make the connection, you're free to actually talk to the hardware. So this is an example of, initialization you may need to do the hardware. You can do at this point. Okay, next in the constructor, you need to create a ASIN motor axis object for each physical axis you want to support. The number of axes usually comes from the create controller command. This is the Doxygen layout of that. The call, the pointer, the ASIN controller, and number of axes. And last thing this particular one did, and something you need to have in your constructor, is you need to start the polling task. And the arguments are going to be the moving period and the idle period, which again you get from the create constructor. Let's see, the third argument, force fast polls. I think it looks like that's an argument you can give it if you think you need to prod the hardware a few times before actually make a connection.
No, what it is you tell the motor to move, and then you ask if it's moving.
Oh, so
if it is, that will speed up the polling test.
I see.
But sometimes the first response you get back, it hasn't yet said it's moving, and now it would wait a whole second, for example, to do the next poll.
Okay.
And you don't want to do that, so it forces it, say, to do 10 quick polls. Once it should be moving, at least, quickly ask.
Okay. All right, so yeah, the force fast polls, that's an argument that's used when you're in a moving state to make sure you get the moving indicator from the hardware as soon as possible, not having to wait for the full polling period. It kind of lets you poll at a more leisurely period than what you would normally, and still get fast response for moving done flags.
Just go back to that. There's one other point, that this start poller is a method that's implemented. It's a virtual method in the ASIN motor controller base class.
Right.
It's probably sufficient for most controllers. All it does is to loop over the number of axes and call their poll method, and then if any of them say that axis is moving, change the poll period, or not moving, change the poll period appropriately. But if there's something that you need to do in your controller poll rather than just per axis, you can re-implement that method.
Okay. I did want to give an example of creating the methods for the custom parameters. So in this case, ACR had a parameter that required the right float 64 method. So it is going to catch those ASIN, that ASIN event, and so again, yeah, it's called memory ASIN client. Calls ASIN float 64. It gets the function for why it was called, and it gets a pointer to the axis. In this instance, the function it wants to implement is a jerk function. So it tests the function. It sees that it's ASIN jerk, and it performs the operation to set that parameter. Otherwise, if it's not the function that it's looking for, it just passes it through to the ASIN motor controller, back to the base class, basically. And I guess a rule of these functions is you want to perform a callback. So that's kind of the controller side of it, constructor. Now I'm going to start with the axis constructor. So what are we doing with the axis? We're creating an object that's, again, it's going to be customized for a particular motor controller. You can initialize the hardware at this point also. You can also characterize the axis. You can push parameters back to the motor record that describe the hardware that it needs, such as, main instance of whether it's capable of doing closed loop or it has an encoder feedback. And then I guess not really in the constructor, but as part of supporting this class, you need to implement all the methods that the motor record expects to be functioning when it's moving hardware. Move velocity home, set position, etc. You also, as part of that, you implement a report method that is called, there's an ASIN report call that can give you the information on the hardware. So back to our example, the ACR. So this is, again, this is called from the motor controller constructor for each axis with the arguments, with the axis number and the pointer to the base class. This kind of describes it. So I'll start with the methods. The first one is move. The arguments are coming through the device layer from the motor record. So if you're moving, you need a position you're moving to. You have a flag for whether it's absolute or incremental. Min velocity, which I believe corresponds to the base velocity in the motor record. Maximum velocity, which is the slew velocity of the motor record. And acceleration. This is this is what code is going to look like in this method. You're basically passing these parameters through to the hardware. In this case, it's an ASIN octet, so you're writing to the controller. They're going to be ASCII strings. You can again check in the flag for relative absolute, and it's going to require different calls to the hardware. So these are the commands you're going to find in the motor controller's programming manual. So I won't go into code in the rest of a lot of these. Move velocity, it's the same situation. You're getting called from because of a event in the motor record, so you're getting passed those parameters, and you're passing them on to the hardware. The pole, so this is, so I believe this is the function that gets called when you do create the polling task. This is you do have to implement this for every controller.
Right, it gets called in the polling.
Right.
For each axis.
It does get passed one pointer to a moving flag. I'm going to kind of go through the code on this just to give you an instance. In this case, you're reading position. You're reading the position with a write read to the controller. You get that back in a string, which you set a variable to, and this set double parm. This is where you're actually passing that position to the motor axis base class.
Well, it's actually the motor controller.
That's a controller? Okay.
Yeah. So each axis has a pointer to its controller.
Okay.
Which is PC.
And the ASIN motor takes care of getting that value back into the motor record. This example of getting a moving done flag from the hardware. Losing my mouse. And also included other common polling status you need to keep track of is the limits. The last thing, there is a motor status problem flag you need to set. If there's a problem, again, that gets reported back to the motor record, and it'll display that in the MEDM display. So another method, home. You need to implement this if your hardware is capable of doing homing. Min-max velocity. Min is probably base, max is there's a home velocity on the motor record. Acceleration. And in the motor record, there's two homings, there's a forward and a reverse, so that flag gets passed in this argument, whether you're homing forward or positive or negative. The report method, again, you're going to this gets called when there's when someone's at the OutSy console prompt and either doing a DBIOR, which I think gives you the controller report method. There's two methods. It's a controller report and an access report. I think the access report gets called when you do the ASIN report call to that particular access.
So typically, there are different levels. Level 0 is the tersus report. Level 1 would be an additional level of detail. Level 2, an additional level of detail.
Is there any kind of, I don't know, recommended level or just?
For ASIN port driver, there is some recommended stuff. Like if it's a multi-device, has multiple addresses, like multiple axes, I believe if you call it with level 1, it will only report on the first device and not on all 8 of them. Higher levels will do all the sub-devices as well.
Set position method, again, that's a motor record function where you're setting the position. This gets called, and with the new position, you need to set the hardware to. And the stop. It's very critical you get this right. And this, again, is coming from a directive from the motor record. And I think that's it. Any questions?
Is there anything like an abort or anything, or is that just a
I don't think the motor record. I mean, you could implement an abort, but you'd have to use you have to be outside the motor record, I think, to do it. But you can implement stop as you can implement stop as either a dead stop or normally you do a controlled stop, which I think would be equivalent to an abort, where you actually decel to a stop. But a lot of controllers let you stop instantly, which you're going to lose position if you do that. But the motor record only has the one stop call.